Okay, here is an example, and we're going to draw Morhs circle for a bar that has an axial load on it. So we're told that the bar is 10 millimeters thick, and it has this 180 kilonewton load on it, and we're supposed to find the maximum normal stress and the normal and shear stress in an element rotated at 57 degrees. So when we have an axial loaded bar, the maximum normal stress occurs along the x-axis because it's in purely loaded along that x-axis. No shear and no stresses in the y direction. So then to solve this, we just do what we did in chapter 1, and we have sigma max equals P over A. Our P is 180 kilonewtons. I'm going to change that to newtons. So I have 180,000 newtons over our area is the width of 120 millimeters times the thickness, which is 10 millimeters. And we get that the maximum normal stress is 150 newtons per millimeter squared, and newtons per millimeter squared equal megapascals. Maximum normal stress, but pretty simple. If we drew a stress block of that like we did on the bar, we would just have two arrows on it. They're in tension, it's positive, 150 megapascals. That's what they both equal. Okay, so now we're supposed to look at an element at 57 degrees. So this element looks something like that. And on this element, now we're going to have a shear stress in some direction. And we're going to have a sigma x and a sigma y. So now we have three stresses to solve for, because all the shear stresses equal the same thing. In chapter 1, we did this, which would take a long time the way we did it in chapter 1. Chapter 1 method, we would have to calculate the normal and shear stresses at 57 degrees using inclined plane method. And then we would have to then calculate the normal and shear stresses at 33 degrees, because that is the perpendicular angle. So that would be a lot of calculating. We'd have to calculate all those areas and blah, blah, blah. So we're not going to do that. We are going to use Morhs circle. So if we draw a Morhs circle for what we know already, which is that we know that our right face here, if we look at the right face, well, let's just, so Morhs circle. we have a procedure. So, step 1 of our procedure is the center of the circle. And that just equals the stress in the x direction plus the stress in the y direction over 2, the average of the two stresses. So that equals 150 megapascals plus 0 over 2, and we get a center of the circle at 75 megapascals. Okay, step 2 is to identify a point. A point is a combination of a normal stress and a shear stress. So, from our drawing here, if we look at the right face, so use right face of stress block in A. So then our normal stress is 150 and our shear stress is 0. So that's the point on our circle. So now we know the center is at 75, our point is 150 and 0. We also know that there's no stresses in the y direction, so that will be 0. So we can draw our Morhs circle. So we draw this is the stress axis in megapascals. This is the normal stress axis, I guess. This is the shear stress axis in megapascals. We draw our little arrows to help us with our plotting. So things plotted above the sigma axis. Shear stress is above the sigma axis. We'll rotate that face clockwise. Shear stress is below the sigma axis. We'll rotate the block counterclockwise on a given face. Okay, so if we plot 150 and 0, so let's do each point is worth 2. So 1, 2, 3, 7.5. Okay, so this point is 150 and 0. Then we have our center of the circle is at 75. That'll be here. So this is 75. And then we know the radius will be 75 just from knowing how circles work, but we can also calculate the radius off to the side. So the radius equals sigma x plus sigma y over 2 squared plus tau xy squared and the square root of all of that. So we get that R equals 75. Okay, so then we can draw our circle. Oh. Okay. That worked out pretty well. Okay. So we have our circle. We know 2 points on it. 0, 0, and 150 and 0. These are also our principal stresses. So this is sigma max, and this would be sigma min. So from this, we have our principal stresses as well. But the question is to the normal and shear stress rotated at 57 degrees. So that would be 57 degrees in real life. This is theta equals 2 times 57 degrees on Morhs circle. So 2 times 57 degrees equals 114 degrees. And we're going to rotate that counterclockwise. So what we're doing here is up here we're taking this block and rotating it 57 degrees this way. So we go from block A to block B. Okay, so we draw that on our Morhs circle. So we have a line, 57, so 45 degrees would be here. 57 degrees is maybe something, or 100, I guess this is 105 degrees, sorry. So this is 90 degrees. And we'll say that this is about 114 degrees. So now all we have to do is to calculate this point, sigma x and tau xy. Okay, and I'm at the end of my page. So let's bring our Morhs circle. Oh, I forgot the label. We'll bring this to the next page. Okay. Here we go. So now we know, now we get to use geometry. So to find these points, we need to know this distance here, and then we'll need to know this distance. So this we'll call A, and this we'll call B. So if this angle equals 114 degrees, then this angle here equals, so we would have so we would take this angle is 114 minus 90, which equals 24. And that angle equals this angle. So this is 24 degrees. So we can find, here? Prepared a little bit more. So we have to use, so we can find that we know R, which is this distance. So this is R along here, and we know the angle. So that way we can calculate what B and A are. Okay, so what was R? R was 75 megapascals. Copy. Paste. So if R is 75 megapascals, then A equals 75 megapascals times the sine, it's opposite, of 24. So A equals, I don't have this value, so let me calculate it quick. A equals 75 times of 24 degrees. So this is 30.5 megapascals. And B equals 75 megapascals times the cosine of 24. So B equals 75 times cosine of 24 equals 68.5 degrees. Or 68.5 megapascals. Okay. And that equals our tau xy at that location. To find the normal stress at that location, we have to do a little bit more math. So we know to find what sigma x is, we have to take where the center is. So we go from that point, center, minus A. So we get a sigma x equals 75 minus 30.5. Those are both megapascals. We get 44.5 megapascals. Perfect. And that is our sigma x. Okay, so then we can start drawing our stress block. But we also need to know this point, because this point is 180 degrees away, which means it is 90 degrees in real life. So this point is sigma y tau xy. So it's the same tau xy, it'll just on the y face rotate the block counterclockwise. So to find sigma y, we would have these same distances A and B. So sigma y is just C plus A. So sigma y equals 75 plus 30.5, and that equals 105.5 megapascals. So now we know our sigma y, we know our sigma x, and we know our tau xy. So we can draw our stress block. And we rotated 114 degrees on the diagram, on Morhs circle, which was 57 degrees in real life. So we start by drawing our original right face, which was vertical. We went counterclockwise 57 degrees. And then just really bad at drawing these. Oh well, you get the idea. So this is 57 degrees here. And then we just label all of our parts. So sigma x is a positive 44.5 megapascals, so that means it's in tension. If we look at that point on Morhs circle, it's above the x-axis, so it's going to rotate the block clockwise, so we draw it down. Then we look at our sigma y point. That was 105.5 megapascals, also positive. So that's coming out here. 105.5 megapascals. That point is below the x-axis, so it's going to rotate it counterclockwise. So, just like we talked about, that shows us the tails match. And we have this equals 68.5 megapascals. And then the arrows point towards each other. So we can finish off the block. This is equal and opposite. So that's also 105.5. And this one is 44.5. So that is our stress block. Much easier than what we would have had to do with all those equations once we get comfortable with it.